Okay, in today's video, I'm going to go ahead and walk through a few of the questions that you guys asked for extra help on from Worksheet 4, preparing for the Chapter 5 test. In this problem that we see here, we are asked to factor this. Now, when we first look at what we see here, this follows a regular quadratic pattern. So if I were to have given you the problem a squared plus 2a plus 1, chances are you would have recognized right away that we could factor that into a plus a times a plus a, or a plus a quantity squared. Well, what you need to recognize here is that the part that we see right here in the middle, this cosine, I went a little bit too far with that. The cosine of 2x is actually the variable in this problem. And then what we see here, when we see cosine of 2x squared, that is the variable squared. And so in this case, you can treat the cosine of 2x like how we treated the a over here, meaning that this factors into cosine 2x plus 1 and cosine 2x plus 1, or we can write that as cosine 2x plus 1 quantity squared. Now, to further simplify this even more, we want to recall that we have an identity for the cosine of 2x. So what we can do is we can replace this with the identity that has a minus 1 in it. So we can replace that with 2 cosine squared x minus 1. And then if we write the rest of the problem around it again, then we are left with this. And now the minus 1 plus 1 cancels, and we just have 2 cosine squared x quantity squared. And if we distribute that squared to both terms, we end up having 4 times the cosine of x quantity, or x fourth. And there we go. All right, and the next problem we wanted to look at was problem number 5. Okay, so down here in problem 5, we want to find a value of theta that makes the following equation true. Recall that cofunctions are only equal if the angles are complementary, meaning that they add to 90 degrees or pi halves radians. So we can go ahead and take this angle plus this angle and equal it to 90. 5 theta, minus 1. Come on, there we go. 5 theta minus 1 plus 3 theta plus 19 equals 90. We can combine like terms. 8 theta plus 18 equals 90. And then after solving, we get that theta equals 9. All right, next question we wanted to look at is number 6. In question 6, we want to find a value of theta that makes the following equation true. Okay, so one thing that we know about cosine is that when the negative is on the inside, it really doesn't make a difference. Now, there are a couple different ways that we can approach this. Since here we have the negative on the outside, what I would probably do is just figure out what cosine of 3 pi fourths equals. We know the cosine of 3 pi fourths is negative root 2 over 2, and then we have a negative on the outside of that. So if we simplify that, we just get root 2 over 2 equals cosine of theta. So in this point, we're trying to ask ourselves, well, which angles does cosine have a positive root 2 over 2 ratio? Now we know that happens at the 45 or pi fourths reference angle, and cosine is positive in quadrant 1 and quadrant 4. So the two angles that could work for us are pi fourths or 7 pi fourths. Both of those would be correct, or their equivalent answers in degrees. However, since this problem started in radians, we should probably give our answer in radians. All right, looking at number 7, we see we have sine of negative theta equals 5/7, and negative theta is in quadrant 2, and we want to find secant of positive theta. Now, you really need to pay attention to when we switch back and forth between negative theta and positive theta. Since the final answer that I want to find is for secant of regular theta, we need to figure out where the heck regular theta is. So first of all, let's work with this. If we know that negative theta is in quadrant 2, that means that I went backwards enough to be all the way into quadrant 2. So I essentially went backwards, not 90, not 180, but more than 180 degrees. So if I were to find that same angle going forwards, well, then I would go forwards 90, 80, and then a little bit more, which would put me into quadrant 3. So if negative theta is in quadrant 2, then positive theta is in quadrant 3. All right, so now that we know that we're in quadrant 3, we know that our secant answer will be negative. Okay, now let's come back over here to this fact that we have about our sine function. So we know that sine of negative theta equals 5/7. So we know with our sine function that if the negative is on the inside, it cannot be ignored. So that means sine of regular theta equals negative 5/7. And since I know that I'm in quadrant 3, then that makes sense. So now I can find my x, y, r for regular theta. I get negative 5 for y. I get 7 for r. And then after doing my Pythagorean theorem, I have 49 minus 25 equals 24. I square root that, and I get negative 2 root 6. Okay, so now I'm going to go ahead and I'm going to, let's see. What happened? Sorry about that. Not quite sure what happened, but anyways, we're back. So now I'm going to go ahead and I'm going to find secant. And I know that secant of theta is equal to r over x, so I will have 7 over negative 2 root 6. And if I rationalize that, then I get 7 root 6 over negative 12. So negative 7 root 6 over 12. Now, an alternate way to solve this is to use the identities. And that's the way that I solved it on the worksheet answer key. And in this case, what you want to do is you would use the identity that sine squared theta plus cosine squared theta equals 1. And we could use negative theta here if we wanted to. And we would get 5/7 plus cosine of negative theta squared equals 1. And then we could go ahead and solve this way. Now, in this scenario, we know that cosine of negative theta and cosine of theta are the same because of our negative angle identities. And after solving here, we end up getting that cosine squared theta equals 24 over 49. Therefore, cosine of theta equals 2 root 6 over 7. Because we know it's in quadrant 3, we know it is negative, and then we can find the reciprocal to get our secant. Both of these ways work. I think, however, the way that I did first probably matches more how we've been doing the problems in class this year. Okay, let's go ahead and take a look at number 10. All right, so looking at number 10, we want to go ahead and find the tangent of 285. Now, remember that you can use any two angles that add up to 285. You could also even find the negative angle that would be in quadrant 4 if you'd rather do that than working with these larger angles. It's all up to you. So two angles that make 285 would be tangent of 240 plus 45. And if we expand this out with the formula, we will have tangent of 240 plus tangent of 45 all over 1 minus tangent of 240 times tangent of 45. All right, now if we figure out what each of these is, the tangent of 240 is going to give me positive root 3, and the tangent of 45 is going to give me 1. So when I plug these values in, I get root 3 plus 1 over 1 minus root 3. And I can't leave my answer like this. I need to go ahead and rationalize that. So I multiply it by 1 plus root 3 over 1 plus root 3. And when I simplify this in my numerator, I get root 3 plus 1 plus root 3, which gives me 2 root 3 plus 4. And then in my denominator, I'm going to get 1 minus 3, or negative 2. And like we talked about in class, we can go ahead and we can simplify all of these numbers that fit inside the heart. So we end up being able to divide both of them by negative 2, giving me negative root 3 minus 2 as my final answer. All right, next up is number 16. Okay, number 16 is kind of tricky because we don't have a formula for cotangent. We do, however, have a formula for a tangent difference. So we could think of this like 1 over the tangent of pi minus theta. So essentially what I can do now is I can do this formula in reverse. So it's kind of like doing, if I were to do 1 over the whole fraction, So tan pi minus tan theta over 1 plus tan pi tan theta. When I divide by a fraction, it's the same as multiplying by the reciprocal. And so I can rewrite that in this format so that I'm not dealing with a complex fraction. And then from here, whenever you have those angles that are on our unit circle, our intention is for you to go ahead and fill in their values. And tangent of pi is going to be equal to 0. So that whole term gets canceled out as does that term, leaving me with 1 over negative tan theta. And when I have a tangent in the denominator, that's the same as a cotangent in the numerator. And that's how I get negative cotangent of theta as my final answer. All right, next problem we're going to look at is number 27. Okay, so when we get down to 27, there are a couple ways that we can do this. And if you look at my answer key, you'll see that I did go ahead and work it out on both the left side and the right side. I'm going to start here with the left side. Okay, so if I were to take this and rewrite it in terms of sine and cosine, I would have sine squared x over cosine squared x minus sine squared x. And at this point, I want to make a like denominator so I can add these fractions, or subtract the fractions. So I'm going to multiply by cosine squared x over cosine squared x, giving me sine squared x minus sine squared x cosine squared x all over cosine squared x. Now I can see, well, the sine squared x is a common factor, so I can factor that out. So I'm going to go ahead and factor that out, giving me 1 minus cosine squared x over cosine squared x. And then from here, I know that I can replace the 1 minus cosine squared x with sine squared x. So I have sine squared x times sine squared x all over cosine squared x. And then this sine over cosine can be written as tangent. So I get sine squared x times tangent squared x, and I have met my match. Now, let's say you preferred, oh wait, hold on. Then this is the same as sine x, tan x, quantity squared. Okay, now let's say you preferred doing the right side instead. Well, this is essentially going to look the same. We're just going to do these steps in opposite order. So on the right hand side, I would first distribute the squared, giving me tan squared x, sine squared x. And then I would go ahead and there's a couple ways I could do this. One way is I could essentially undo what I did on the left. But an alternate way that we could do this is we could rewrite each of these with their Pythagorean identities. So tangent squared x is equal to secant squared x minus 1, and sine squared x is equal to 1 minus cosine squared x. Now the reason why I did this is because I look at the left side, and the left side has a minus in it, and I need to somehow get these terms to split up into something with a minus in there, which is why I tried rewriting with the identities. Now if I go ahead and FOIL these, that would give me secant squared x. When I do secant squared times cosine squared, since those are reciprocals, that just gives me a minus 1. And then over here, I'm going to have a minus 1, and then I will have a minus, actually a plus, cosine squared x. So now from here, I can regroup, and secant squared x is equal to tangent squared x. And right here, if I factor the 1 out, I have 1 minus cosine squared x, which is equal to sine squared x. And now I have gotten what I'm trying to prove. All right, the last problem that we're going to work out tonight is number 27. Okay, so in this problem I would definitely start on the left, mainly because the left side is much more complicated looking than the right. And I would start by writing this in terms of my sines and my cosines. So I would have 1 over cosine x minus sine x times sine x over cosine x. And the advantage of doing this is I see that they both have a cosine x denominator. So I have 1 minus sine squared x all over cosine x. And then we can do a substitution with that Pythagorean identity. Cosine squared x over cosine x. And then we can cancel off a cosine, leaving me with cosine of x. Now, a few tips when you're doing these verifications. First of all,